The first speaker is Professor Weizhu Bao from National University of Singapore. His research interests are very wide. So his interest is Bose-Einstein condensation, computational fluid dynamics, computational quantum physics and chemistry, multi-scale modeling, simulation and application, numerical analysis, and scientific computing. He got a Pen Prize in scientific computing last year. He has been very active, and he has over 100 papers in leading journals. Professor Bao's today's talk title is Mathematical Models and Numerical Methods for Bose-Einstein Condensation. Please.
Thank you. This one? This one. Okay, first thank the nice introduction, and also I would like to thank the organizing committee for the kind invitation, and it's a great honor for me to be here. And a brief outline. I will begin with what is Bose-Einstein condensation, or BEC in short. It's a theoretical prediction, experimental realization, and mathematical models, the gross-split equation. Then I talk about the ground states, which is kind of constrained minimization problem or non-linear eigenvalue problem. Then I talk about dynamics, a kind of dispersive non-linear PDE. Then I talk about how to extend a simple system to BEC in rotation frame with non-local interaction and spin-orbit coupled system. Finally, some conclusion. Okay, so the BEC can be traced back to 1924 when Bose studied black body radiation. He proposed a new statistics, means two photons can be counted as either identical or different. So this is so-called Bose statistics or Bose-Einstein statistics. He wrote a paper, but unable to be published. Then he sent a paper to Albert Einstein. Einstein was very excited about the result, the statistics. Then Einstein helped him to translate into German and publish it here. And also, in addition, Einstein applied the statistics to a system of n particles, non-interacting, but for bosons instead of photons. And he derived the following so-called Bose-Einstein distribution in cold gas. Here, T is temperature, and Kb is Bohr constant, and the system chemical potential is mu, and with different energy level epsilon I. So this Ni is basically the proportion of number of particles in a system with energy epsilon I. So from this distribution, so Einstein observed makes the following prediction. You can see if T is large, we will see the distribution of the fraction of particle to the energy level epsilon I is a smooth function. However, there is a critical Tc, which depends on epsilon 0 minus mu over Kb. So when T less than Tc, this is roughly nanokelvin. Then in a system, almost most atoms, they stay the minimum energy state. They stay at the energy level epsilon 0. So you can say most atoms are here. So based on this one, Einstein makes the following prediction or conjecture. He says at 0 or low temperature, most particles behave in the same way at the quantum mechanical ground state or minimum energy state. They show a gregarious behavior, and he said basically when temperature decreases, there's a quantum phase transition happens at extreme low temperature, or they generate quantum gas. They form a superatom, or now we call it the fifth matter of state. So after Einstein had this, so this shows some physiological behavior of particles. At a high temperature, every particle, every atom, like a particle, or we call beta balls. At a low temperature, atoms starting become like a wave. At like a critical temperature Tc, many waves, they overlap. They form some kind of partial condensate. At T equals 0, they have a pure condensate. You can see from high temperature to low temperature, there is a phase transition from random motion to the one single particle state. So since Einstein was very famous, his conjecture, his prediction was studied by experimental physicists, so that to be awarded by Nobel Prize. After 70 years hard working, and it was a realized experiment by using rubidium in 1995. This is a cover picture on Science. And you can see at high temperature, like a 400 nanokelvin, most atoms, they are random. So what is the background? At about 50 nanokelvin, about 5,000 atoms, they behave in the same way. They form a condensate. Okay? And so you may ask, this experiment cost 70 years to be realized. Why? Here shows some difficulty. One is it must be realized at extremely low temperature, at almost zero temperature, and also it must be realized in low density in gas. Because this is density, this is the temperature. You can see at a high temperature, most materials is in vapor or gas. While at a high density, most material are liquids or solids. The BEC is only stay here, and it's in gas at low density, low temperature. And you can see from here to here, there is a curve. Along this curve, the system is at thermally unstable states. So you need to go somehow from this way. So some kind of experimental technique used in achieve BEC, among them are laser cooling, can 3 laser to cooling the atom to microkelvin. Then there's a magnetic field to hold the atom so that the atom will not leave the chamber due to kinetic energy. And then the last step is we call evaporative cooling. Like you want to cool a cup of coffee, you put the cup, you run. The hot molecules will fly out of the system and the remainder become colder. With this technique, it was realized. So then you can see this on Science Journal, they claim 1995 as the molecular of the year due to this BEC achievement in experiments. And after then, there are many groups like JELA in US, NIST in US, MIT, ENS in France, RISE, ETH in Switzerland, Oxford, PKU in China, in US, Japan, Korea, many places. And 3 physicists, this Carl Wieman, Eric Conner, and Wolfgang Cattell was awarded the Nobel Prize in 2001 for this achievement. Okay, and here I list some kind of typical part of BEC, like this kind of pattern has been realized experiment. Typical temperature, density, number of atoms in the nowadays come up to a million to billion atoms in one single condensate, and a special size and a lifespan. Okay, here just a brief summary of a milestone experiment in physics. The BEC was predicted by Einstein in 1924 and for 9 inherent atoms. Then in 1938, London and Chisava linked BEC and superfluidity to show interaction particle system. And 1995 experimental realization in ultra-cooled gas of alkali atoms. Since then, BEC became a new era in atomic, molecular, and optical physics and quantum optics, and also attracts interest of computational, applied, and pure mathematicians. And some famous physicists here, like many Nobel laureates, have did great work in this field. Okay, so in order to study BEC, theoretically, we need mathematical models. So here shows, you can see, at low temperature. So T equals 0 or T below Tc. We know this is a physical system of n particle with quantum effect at low temperature. So it's kind of can be used by the linear Schrodinger equation with 3 n+1 dimension. N is number of particles equal to million or billion. So since here they are condensed, so every particle behaves in the same way. So you have by using the Hartree ansatz with a mean field theory, we can derive a kind of gross spatial equation or GPE in short. I will review this one in a minute. Of course, if you want to model a system for all temperature spectrum, from high temperature, like every part, all the parts are non-condensed, you need a quantum Boltzmann mass equation. If in between, partial atoms are condensed, partial are non-condensed, you need a coupling. It's a quantum Boltzmann mass equation and the GPE. Of course, if the system is at ground state, at the BEC, pure BEC, we can use a GPE to model it. So you can say, basically, if you want to do a whole temperature comparison, it's a multi-physics, multi-scale problem. So today, I'd like to mainly focus on this part. So we consider a system with n identical bosons. This is a n-body problem. Here, psi n is the wave function of the n particle. This here xj is in R3 and means the position of the jth particle. So they follow this linear Schrödinger equation, and with this Hn Hamiltonian equal this one, kinetic potential of the system and the interaction of any two particles. And since at a extreme low temperature, since most atoms they behave in the same way, so we can use this Hartree ansatz. So the n-body wave function can be approximated by a product of single wave function. And then, since this system is dilute, so the interaction, this guy can be approximated by using Fermi interaction. Basically, this function is a constant g times a Dirac function. So then, the system has total energy for n-body is this one. The psi bar is counted psi. Then you plug this ansatz and this guy into here with this h by using so-called integration by parts for this guy and split integration for each xj. Then this energy functional can be approached by n times E of psi. Psi is, we call this E psi is energy per particle of the system, which is given by here. This is a kinetic potential and the interaction of the but basically, each particle will interact with the other n-1 particle. So, of course, the correct is n-1, but since n is very large, we'll by this one. So this is the mean field. In fact, to mathematically justify from this n-body energy to this one-body energy when n go to infinite, it's done by Lieb and his collaborator in 2000 for ground states. For dynamics, with this energy, we can use a second quantization or write down the Heisenberg equation. You end up with this dynamic equation. And again, for justify from this n-body equation linear Schrödinger to this one-body problem through this ansatz. This was done just 4 years ago by Aldous, Schilling, and Young. They were part in Arnold's math. So basically, for BEC at ground state and dynamics, this is a starting point for ground state, this is starting point for dynamics. So you can see this here, this h bar constant, or m is the mass of atoms, they are very small. So in order to start it theoretically, we need to do non-dimensionalization of this one. You choose a proper spatial dimension and also time dimension. After do proper non-dimensionalization and dimension reduction, for example, when V is anisotropic, they will end up the following dimensionless GPE. Here, this beta dimension constant is 4 pi n times as over xs. As is scalar length depending on the kind of atom, and xs is a dimensionless unit. Okay, so in fact, this equation, or GPE, or Schrödinger equation with cube linearity, has many other, like laser beam propagation, plasma physics for interaction between electron and ion, or quantum chemistry, or material science, like DFT. I think the third talk will talk about electron structure will based on this model. It's a coupling Schrödinger with Poisson equation. And also optics, biology, and superfluids. Here means fluid flow will flow without friction, means superfluids. Okay, so basically, let me summarize the simplest model for BEC at a low temperature. This is a model. Here, psi is a complex wave function, and V is a given real potential, and the beta is a dimension constant. If beta equals 0, means linear, one particle system. If beta large, positive, means repulsive interaction, and beta less than 0 means AS less than 0 is attractive interaction of forecasting Schrödinger equation. Basically, beta equals 0 was written by Schrödinger, and the beta 90 derived formally by physicists Gross and Bielski. Okay, so this system has some good properties like dispersive and time symmetric, and also time invariant. Means you replace V by constant alpha, the density doesn't change. Because in fact here, this rho, the absolute square, means the probability of in time position x, in space x, and time t to find the particle probability. And mass conservation and energy kinetic potential and this interaction energy. Okay, to compare the experimental result, which is ground state. So in this dispersed system, we can consider the stationary states. You try this kind of separation of variable solution. So this ansatz, mu is a constant. You plug this guy into this equation. We end up with the following nonlinear eigenvalue problem. Find the mu and the phi together. So this one with this constraint. So this equation also called as time independent GPE. Okay, you can see if beta equals 0, this is a standard Sturm-Liouville problem. All the eigenfunctions are orthogonal, and for dynamics, superposition is valid. However, if beta is non-zero, then the different eigenfunction might no longer orthogonal, and the dynamics superposition is no longer valid. Means if initial data you expand at different spectrum, then during dynamics, resonance may happen. Okay, and for this pair mu and phi, if we know the eigenfunction phi, you can multiply phi conjugate of phi at both sides. The integration over Rd, you use this one, you end up with this mu eigenvalue, or physically called chemical potential. Comes from this one. Here, this E phi is nothing but the eigenfunction of your Schrödinger equation. You can the ground state is defined as you minimize this eigenfunctional for all phi. Phi in this set S. S is for all phi, the L2 norm equal 1. We know this S is an infinite sphere with a sphere for function of phi as infinite dimension. Okay, and we know this S is non-convex. So this is also called a non-convex minimization problem, or we call constraint minimization problem. So now the question, and also is all the Lagrange equation of this guy is this one here. Okay? So now the question is, given potential V, real function, given a constant beta, is there a minimizer of this one? And is it unique? Of course, we know if phi g is a minimizer, then phi g times any constant exponential I theta 0 for fixed theta 0 is still minimizer. Okay, we have the following theorem. For if V bounded below and confinement, means we go to infinite far field, then if either this one of this condition is hold, then we can prove that there exists a ground state. And also, any ground state can be written as the phi g can be written as phi g times exponential I theta 0. That means for this case, for each ground state, the phase is special homogeneous. And if beta greater than or equals 0, the non-unique ground state, this phi, absolute phi g, is unique. In addition, if the potential V is locally L2, then the non-unique ground state is strictly positive, and the decay is exponentially fast in far field. Here also, we can prove that if in 3 dimensions beta less than 0, or in 2D beta less than is minus beta CB, CB is the best constant in the Nuremberg inequality, then there is no ground state. Okay, and some due to time, I do not skip it. Basically, the idea here is just you introduce a new function of E2 times rho, which is rho equal for any phi. You define rho is absolute phi square. Then for this E2 times rho, which is bounded below, so and this condition and the convex and this one, specifically this set S, if written in phi is non-convex, but written in rho is and this the L1 norm of rho equal 1, which is this set is convex. So you can prove it. And for the non-existing result, we can choose a sequence of function phi epsilon. When epsilon goes to 0, the E of phi epsilon go to minus infinite, so no boundary below. Okay, and also in order to compare with experiment, given potential V, given beta, we need to compute the solution numerically. So the idea is just choose from time tn to t, time step tn to tn plus 1. You first ignore the constraint. You apply steep distance method. You do this one variation, you end up this gradient flow. Then you from time t into at the end of t n plus 1, you do a projection. Just find its L2 then projection. Basically, for example, if this is phi g, we start from phi 0. We go evolve this gradient flow for one time step. Go inside the circle. Then at the end of this one, you projection back. Then continue. You get a sequence. So this equation can be also derived formally from the original GPE by let t equal I tau. We know t is time, so tau is called emergent time. So that's why this method is also called the emergent time method in physics literatures. So question now is, in order to get phi g, we get a sequence. Phi 0, phi 1, phi 2. We hope when this phi n will enter infinite, its energy decreasing, so we get a ground state. Okay, you can easily see from phi 0 to phi 1 height, this gradient flow, the energy decreasing. However, since it's phi 1 height, its autonomy less than 1. So from phi 1 height to phi 1, energy increase. We need to compare these two. So joined with Chengdu and the other, we can prove that if beta equals 0, for any phi 0 and time step delta t, we can prove the sequence and decreasing. And for beta non-zero, we can let delta t go to 0 from this algorithm. We end up the following we call normalized gradient flow. Here is for any t. It's a kind of differential integral equation. For this equation, you can see it needs to prove that the autonomy of phi is conserved. However, the energy is decreasing. Basically, this non-local problem kind of in between Ginzburg-Landau and Schrödinger. Ginzburg-Landau is there where the autonomy and the energy both decrease. Schrödinger both conserved. Here, mass is conserved, energy decreasing. So you can see, if for this method, even for nonlinear case, if delta t is small, by using this one, give the justification that the energy will decrease. Okay, so in order to compute numerically, we can apply your favorite find a difference, find an element of special mass to difference this one, and for this guy, you must use a backward Euler instead of Kronikson or forward Euler. So you can choose time step as large as possible. So here I show some results. So this is a case, first case. I choose dimension 1, I choose potential V equals 0 at 0, 1, and infinite outside. We call box potential. You can see, in this case, if beta equals 0, the ground state is square root 2, psi impacts the linear problem, like this one. Then, when beta increases, the ground state becomes roughly almost 1 everywhere, and there are boundary layer here, boundary layer here. This shows, basically, physics means if beta large, number of particles is very large in the system, then the energy per particle becomes increased. So energy particle has probability 1 to stay in the interval everywhere. And another case is if this is d equal 1 and v of x equal x squared over 2, harmonic potential. Again, when beta equals 0, the solution is a Gaussian 1 over pi to power 1 over 4 exponential minus x squared over 2. So like this one. Again, you have a trap here. So again, when beta large, ground goes like this one. They call Thomas-Fermi approximation solution. Here I show the contour of the ground state is 3D with optical potential for different number of particles. Particles small, large, and very large. So in this case, you can see the ground state looks like a multi-scale structure, layer structure, and like this one, very complicated. Okay, so after we have ground state, we want to study dynamics. So basically here, this %0 could be a ground state with a given potential V and some constant beta. The dynamic means you have this initial data. In experiment, you have ground state, then you change your trap, or you change the number of particles in the system. So there's some mathematical theory and the numerical methods. Okay, this shows if V is subharmonic, the center root of the up to center root of V up. So the higher order derivative up to second order is bounded. And then the %0 has some regularity. So this is a local, there is a time t star, t max, so the solution has a unique local solution. In addition, if there's for V and beta, the potential and the constant beta, if there's ground state, then there's a global solution in H1 normal sense. Okay, also if beta less than 0, and the potential V says this one. For example, if V equals 0 or V is harmonic, quadratic polynomial, this is satisfied. Then if psi 0 is, so its variance is bounded, Then, if one of these conditions is satisfied, we show that there are finite time blow up. There is a Tmax finite. When t equals to Tmax, the h1 norm of the function or L infinite of the function psi will go to infinite. This is very easy to prove by using so-called various identity delta Vt. You can see you can derive if a precise function of the problem delta Vt follow this one. Then you can see you can use to prove that this T star finite, so that the delta Vt star equals go to 0. Then they also use this uncertainty principle. This basically shows if psi use the model to guarantee a particle, quantum particle. Then if psi autonomy is 1, this is the velocity, this is the position. So position time velocity is bounded below. You can say if at T star, this can go to 0, this can must go to infinite. So very easy to get this blow up result. Okay, so with this basic theory for dynamics, in order to start to simulate dynamics and also to see is this blow up, what happens in experiment? Is this blow up from physically or due to some kind of model approximation? Remember, already as an n-body problem, we do model reduction. We use the mean field. So we're using this kind of very nice time series method. Basically, solve this one numerically. You have to first use a time splitting. You first solve free Schrödinger equation because this is a constant coefficient. You can do. We know this operator is an eigenfunction in unbounded domain. It's very easy to be found. So you solve this. This one in space by special method. Then in phase space, the linear system is decoupled constant coefficient. So you can integrate in time exactly. For this non-linear ODE pointwise fixed x, easy to show that the absolute psi, the density, is unchanged analytically. So you plug this back into here, you get a linear ODE, you solve in physical space, you get this one. So you couple this together, you get a very nice, simple, and efficient method. With this method has a good property, has a lot of property, like the continuous problem. So with this good method, we try to use it to study so-called a three-dimensional collapse and explosion of BEC. The physics is this one. We know in this model here, if beta less than 0 in 2D or 3D, there are finite blow up. So this model, mathematically, this model tells us there are finite blow up. So physicists want to know what happens near the blow up. So they start an experiment. So what they do, they take the rubidium and cooling down, get a ground state with a repulsive interaction. Then at t equals 0, they change the interaction from repulsive to attractive by using sort of fishbone resonance. And then they study the count, because this is some snapshots of the experimental results. There's some jets form, and also they count the number. This is time t. This is the number of particles in the system. Initially, you have 16,000 atoms with a repulsive interaction ground state. At t equals 0, they change the beta from like a positive A initial to A collapse negative. This is the kind of number of particles, the dots is from experiment. You can see number of particles in the system, they conserve for a short time t evolve. After that, number of particles decreasing. This shows this system, this model will fail after this t evolve because we know this model mass is conserved. Experiment tells us the mass is not conserved. They ask why. Because to derive this model from n-body system by mean field, you assume the gas is dilute. So that means that the distance per particle is not too small. When beta is negative, right, attracting direction, particle will go to center, and the peak value in the center go to very large when near the blow up time. So at that stage, the so-called the inelastic direction become important. So physicists propose that by adding a quintic here, delta 0 bigger than 0, a damping. Remember here, this I is a common unit. The quintic term can be take care of the three-body recombination loss in the system. With this model, we use the experiment, same as experiment result data. We solve first come ground state, then you do this one. This is experiment without different time step. This is a simulation. You can see this just form. I see it here, and also show the central density, the increase a lot and decrease due to this stamp. Okay, and here we compare. You can see when this A collapse change from positive to minus 30 A0, the circle is the star is from experiment. The solid, the dash is from a fitting from experiment data, and a solid from our simulation. And this is for another collapse parameter. This is another one. They agree very well. After our results, this Eric Kanayer asked our results. And here, this shows, a movie shows how the density change. What I plot here is the absolute cosine at x0, zt. This t was 0. You can say blue is 0, the red is large value. Okay, initially, the trap is cylindrical symmetric. So you can see this is a contour plot. The center is very large. You can see if my t large, if t bigger than 0, since at t was 0, the direction is attractive. You can particle to the center. At the beginning, particle to the center, the central value becomes larger and larger. When it's very large, the quantical damping term will take over. Basically, it's a kind of competition between attractive direction and damping process. There's a sequence of explosion, collapse, explosion, collapse. And from the density comparison, our result agree experiment very well. So this confirm this model and also confirm our numerical method is very effective. Okay, after this simple BEC study, we know the BEC is used to model so-called superfluid. There we know the quantized vortices, kind of topological defects are very important signature. Because this is a BEC without rotation, you can see like a bump. And with rotation, so you can see the model, again, similar by mean field theory. You have an additional term with omega LZ. Okay, well, here you can see if I define P, you have minus I gradient. And L is X cross P. Then this is momentum, this is momentum operator, this is angular momentum operator. So the LZ is a Z component angular momentum written in this form. Okay, with this model, so basically, experiment will have a trap, have 3 lasers, the trap will rotate. Okay, and the observer is a fixed position. So for this model, this omega is the rotation speed. Can be if omega 0, collapse in my first case, simple case. And also has this energy conservation, kinetic potential interaction. This is rotation energy. So psi bar is kind of Poisson. You can see if omega equals 0, if V is greater equals 0, beta greater equals 0, this functional is a convex functional. However, if omega is non-zero, this functional is no longer convex. Okay? And this shows this ground state for different omega. Omega equals 0, omega equals like 0.3, and omega equals 0.5, and omega equals like 0.9. You can see there are many holes as a ground space. This is the absolute precise density plot. You can see each hole is a quantized vortices. At the vortex center, the density is 0, like a vacuum. And each vortex center, the phase has a jump, a topological chain defect. And the ground state, again, with this anti-functional, the ground state defined as minimize of the anti-functional with fixed omega and phi in the set S, which is the L to norm equal 1. And again, now the question is given potential V, given the number of particle omega, and the rotation speed of number of particle beta, and the rotation speed omega. For this problem, is their minimizer? Is the minimizer unique? One can prove that for given potential and a fixed beta greater equal 0, there exists a critical omega c depending on beta. When omega less than omega c, the ground state is the same as omega equals 0. When omega bigger than omega c, the quantized vortices, each blue dot is a vortices, will appear in the ground state. Basically, you fix number of particle, you have a rotation frame. When the omega increase, the so-called quantum phase transition will happen in the dual dynamics, or bifurcation will happen in the energy diagram. Basically, the solution from radial, if V is radial symmetric in 2 dimensions, the solution will from radial symmetric to so-called symmetry breaking solution. This one. Of course, our method can be grossed without when omega equals 0 can be extended to this case here. Okay? And here I show some, what here I show is the ground state for fixed potential, like in 2 dimensions, what I plot here, epsilon psi square density. And with a given potential V in 2 dimensions, with the potential V equal x squared plus y squared over 2, and fixed beta equal 100, fixed number of particle. This is when omega equals 0, the ground state. It's similar as you can see the bump in the the science cover figure. Also it's in 2 dimensions. You can see now, let me omega show the different ground state, how the ground state change when omega from 0 change to 1 in dimensionless units. You can see when omega change from 0 to 1, when between 0 to 0.5, the omega c roughly is 0.555. You can say when omega from 0 to 1, the ground doesn't change a bump, single bump. And omega equal omega c, which is about 0.55, you can say at that omega, there are 2 grounds. One is radial symmetric, the other there's one single vortices. And later, when omega even larger, the number of vortices become more and more. Of course, here the interesting question is, given omega, given beta, is there an upper bound of the number of vortices in ground state? I'll show you again. For this solution, you can see. You can see basically when omega doesn't change, when omega from you can see 0 to 0.5, the opposite same bar. But omega large, there's a change from radial symmetric solution to symmetry breaking solution. Okay. Okay, and this is when omega beta large and omega large. You can see from this is a kind of a ground for different omega. This is no vortices, one vortice, single vortices, several single vortices, and when omega larger is there are sort of a giant vortices in the ground of different omega. And this is experimental results in lab in MIT and Professor Cutter's lab, and these are simulation results. You can see you match these two; they are very close. You can see also interesting here is any 3 vortices, nearby 3 vortices, they form a right triangle. They call Aug14Thu lattice. And you can see interesting here is this is when the potential is so-called the quintic potential. There are sort of inside is a giant vortices. Inside here is almost a vacuum. Okay, for this case, if it's not dynamics, you can see due to this rotation term, this term is no longer constant coefficient. If you solve, you can based on this formulation, you can design some numerical method. However, here we will just show you continuously this formulation is the same as the other formulation, but numerically the problems are completely different. Here, if we say to fix t and x, this we call Eulerian coordinate. Then if we in 2 define this rotation matrix at and 3D this one. Then if we do a change of variable like x tilde equal at inverse times x, you plug this change of variable into this equation. So this solution equation will reduce to this one. You can see the difference here is here there's a variable coefficient omega LZ. Here is a constant coefficient with a time different potential. This is like we call rotation Lagrangian. Simply rotate. This one, the observer fixed here, and this one, the observer sitting with the rotation frame. You can see it becomes this one. So with this one, this kind of time space method can be easily extended. Just show you one example. This is I have a start from a ground state. At t equals 0, I apply an anisotropic potential. You can see the dynamics interest is due to I apply some kind of anisotropic potential. You can see the lattice, each below dot is a quantized lattice. They will rotate and they become anisotropic. And with this this new method, it's very easy to realize from very simple, easily. Okay, next example is for so-called dipolar BEC. There, the particle has a long-range interaction. Basically, you can see, we know as like a quantum chemistry for molecule, and external electrical or magnetic field, then two molecules will form a dipole with a given orientation, like n equals 001. For many, many dipoles, they align along the axis. Then similarly, based on some formula by means of the theory, the model looks like this one, with the last term is convolution, and the kernel U dipole is written in this one here. Here, this n is a fixed unit vector in R3. Okay, and you can see this kernel is highly singular at the origin in R3. You can see near origin, the U dipole roughly is 1 over epsilon x power cube. We know Coulomb potential, Coulomb kernel, quantum Poisson equation in 3D is 1 over epsilon of x. So this is much singular. So I want to ask mathematically, is this convolution mathematically well defined with this highly singular kernel? Well, here you can see, with this one, it's not easy to see, but you can see if we define R equals this one, and dn equal n dot gradient is a directional derivative, and dn equals this one. Then this kernel can be decomposed to a local Dirac function plus this one. And then it's the full function is this one. Then this convolution can be rewritten as minus psi square, local content interaction plus this one with phi is nothing but the Poisson equation. So plug this guy into this equation, so the equation is reformed as a Gross-Podolsky, a Poisson type equation. And its energy can be written this way. From here, you can see the energy is well defined for given n, given beta omega. Lambda, beta lambda is a two-dimensional constant. Again, you can see if interested here is if this V is radial symmetric, is stereosymmetric, strongly confined in this direction, then formally this model can be reduced to two dimensions. This one is similar, but this one must be replaced by minus Laplacian power 1/2. You can derive this fractional Poisson equation naturally from this dimension reduction for physical system. And we can study ground state and dynamics. I just show you, okay, we have, for ground state we have this nice result. And this condition is sharp. And again, let's show you one result. Here, this is ground state when lambda equals 0, no dipole interaction. At t equals 0, let the dipole interaction comes in. I have the following. You can see initially it's a Abrosov lattice set. Every three nearby vortices will form a right triangle. You can see at some time due to this dipole orientation, most of the lattice will align near the dipole orientation. They almost parallel and align as dipole interaction. Okay, our last example is they call spin orbital coupling BEC with this coupling system with this guy for spin orbital coupling with this omega term for so-called internal Joseph junction. And the experiment is used to study so-called topological insulator. And this kind of insulator, if do any topological change, is still insulator. The model like this one, we have some analysis and results for this model. Okay, I have conclusion is I just give a brief model for this GBEC at 0 temperature towards the ground state. Its best method is using this backward Euler-Fine difference method to solve it for ground state. And for dynamics, it's easy to use this time splitting spectral method, which performs very well. And some future problems like a spinel system, like a BEC at finite temperature, and also Fermi condensation, or some non-local interaction of high dimensions. Last but not least, I want to thank my collaborators in mathematics, Peter Mark, who's in the audience, and also in physics, my friend and collaborator, Dieter Jaksch. And thank you for your attention.
Thank you very much for your nice talk. So, are there any questions? I can. Oh, please.
Yeah, when we leave the small interaction regime,
yeah.
When Gross-Podolsky is not valid anymore for BEC, what would you suggest, modeling and numerics-wise?
Well, this is a very nice question. For example, if you leave the small interaction regime, there are a few. One is people try to. One is like a they use this non-classical Schrödinger equation with like a high order interaction. Like you add a Laplacian up to psi square times psi. Or they using like a so-called from n-body problem, using like a so they expand with the ground state and excited states together with a sort of like a Bogoliubov approximation, pop approximation, like this kind of new models must come in. Which is coupled with a quantum Schrödinger type equation, nonlinear, with like a Boltzmann type equation for final temperature.
Okay, I can only accept one more question if you have.
So I have one question.
Yeah.
So when you prove the uniqueness,
yes,
you introduce a transformation from transform a non-convex energy minimization problem to a convex
exactly
problem, right?
Yes.
So do you need to assume the parameter beta is positive?
The transformation can be used without beta can be positive and negative, right? Only when beta greater than equals 0, the new functional, the E tilde rho is convex. You can obtain the unique result. Otherwise, you cannot get any result. Because the transformation is still valid, but from that transformation, you don't see more insight there.
Okay.
Yeah.
Thank you.
Okay, so it's time to speak again.